Hello everyone, good afternoon. Welcome everybody back to the cycle of seminars of the Astronomy department here at IAG. I am very, very happy to have Vinicius Placco, Dr. Vinicius Placco here with us here at IAG. Thank you, Vinicius, for accepting our invitation. Vinicius got his PhD here at IAG itself. He has held several positions throughout his career, most of them in the US, such as Gemini Science Fellow, as well as Research Assistant Professor at the University of Notre Dame. And today, Vinicius is going to present the seminar, Is Carbon Ubiquitous in the High-Redshift Universe? A Stellar Archaeology Perspective. Questions will be asked to Vinicius after the end of his talk. And if you're following us, if you're following the seminar through our YouTube channel, you can also ask your questions. You can write them on the chat. We will redirect them to Vinicius after the end of the talk. And if you're on Google Meet, you will also have the opportunity to ask your questions. And before the seminar begins, I would like to ask everyone on Google Meet to turn off your cameras and your microphones. And Vinicius, you can start whenever you want.
All right, so can you all hear me well? Is it okay at the back? Is it? Okay, good, good. All right, so I see the screen over there, so that means that it's okay to go. Oh, thank you very much, everybody, for being here. Well, I've been at IAG for many, many years. I've been here for, I think, 12 years total. So it's always really nice to come back and see lots of familiar faces, but also see lots of new faces, which means that the department is healthy and lots of new students are coming. So that's very, very good. Thank you, Guilherme, for the really kind introduction. And so my mission today is to maybe try to convince you about how the universe went from this very pristine Big Bang nucleosynthesis type of chemical composition all the way to what we see today in the surface of the sun, for example, right? And the reason I'm highlighting carbon is just as one typical example of a metal that has a lot of effect when you're transitioning from population 2 stars or population 3 to population 2. So hopefully I'll be able to convince you and give you some sort of a theoretical framework as to how and why carbon is important, and then try to frame this into some sort of what I do is an observational perspective. So how do we address cosmological type questions just by looking at stars in the Milky Way in the redshift 0 universe? Before I start, so now I'm at this institution called NSF's NOIRLab, and I just wanted to give you some sort of advertisement and talk to you about what it is. So this is the acronym. So this institution was created about 3 to 4 years ago, and it's an amalgamation of all the open access astronomical facilities in the optical and the infrared to the US. So we manage all of these mountains. I'm sure you know all of these names by now. And the NSF decided to just combine all of this in a research laboratory. So then we're all based in Arizona, in Hawaii, and in Chile, and we manage all of these telescopes, including this Community Science and Data Center, which is a department completely dedicated to data science, software engineering, data archiving, and data curation. So for the young folks out there, we have lots of open positions there. If you want to talk to me about any of those, I'd be happy to chat with you. There's always good opportunities for everybody. All right, so after the advertisement is done, okay, so let's go back to the main topic. So in asking if carbon is ubiquitous, it's a very weird word, in the high redshift universe. So the really short answer is yes, right? I could just end here, and then you'd be convinced that this is the case. However, it depends a little bit on how early we are talking, right? There are many theories that believe that this transition between a chemically pristine universe to a chemically polluted universe with metals, it was some sort of a sharp transition. So there's a stellar generation that evolves, pollutes the interstellar medium, and then the next generation, it's all enriched. But then there's some speculations about the fact that maybe this is some sort of an extended period in terms of redshift that would allow the universe to be a little bit more enriched. But before we start to talk about carbon, let's just talk about the first stars in the universe. So one of the beliefs is that the very first stars to be born in the universe after the Big Bang, again, just out of hydrogen and helium, they would be really massive, right? If you remember the Jeans mass from your classes, that depends on temperature and density pretty much, right? And then you have your fragmentation mass, and then you form stars. But then if you have a universe with only hydrogen and helium, chances are you're forming really massive stars. So this is a simulation of the 100 first stars to be formed in the universe. And as you can see, at really high redshifts, all of those stellar masses or dark matter halos, they tend to form really high massive structures, right? They will not fragment enough to form low mass stars. And this, what you see here on the right-hand side, is just a histogram of those 100 first stars, and all of those are massive. There's one here with 8 solar masses, but pretty much all of those are really massive, meaning that if they're massive, they live for a very short period of time, so then we wouldn't be able to observe them today, right? So this is just one speculation about that. So, and what happens next is, how do you transition from that population, what we call population 3, into population 2? So on the left-hand side here, you see for metallicity 0, so no metals whatsoever, all the way to some pollution with dust. And by dust, think of any metals, right? Anything other than hydrogen and helium coming into the interstellar medium. And what this does, we don't even need to go very far here. Just know that this is temperature. This is density of the gas or the dust. And the diagonal lines here are just the typical Jeans mass for that combination of temperature and density, right? So as you introduce more and more dust on that environment, for a given density, the temperature that you need to achieve in order to form structures decreases, meaning that you're able to form stars that are lower mass, right? So here you have 1 solar mass, 10 solar masses, and here's 10 to the minus 2. So then, as you enrich your interstellar medium with metals, that typical temperature for a given density decreases. So you're forming low mass stars, right? So then it fits our prejudice that, well, once you start having metals, fragmentation occurs, you form low mass stars, and then in principle we could see those today. Because if you form a 0.8 solar mass, main sequence lifetime is billions of years, right? We would be able to see that today. And in the middle panels here, you see that for 3 different star formation efficiencies, as you go from no metals to some metals, you see that you form, I don't know if you can see the really tiny white dots here. So what happens is you're also forming more stars because you have the same mass. If you fragment those a little bit more, you have more stars with the same mass of the gas cloud. And that also affects when you look at the mass function, right? The mass function for a really pristine universe, it's kind of a flat in this particular simulation. And as you go to a metal-rich universe, then you tend to form more low-mass stars. And that fits the bill, right? We observe these second-generation stars. That'd be great. We can observe them today. But is there a chance that we can find today in the Milky Way a star with no metals whatsoever, right? Maybe at that first generation of stars, it follows an IMF. Maybe that IMF allowed a couple of stars to form with 1 or half solar mass or 0.6 solar mass. So maybe that we have speculations that this may be the case. And I'll talk about this in a moment. So there's another simulation here. And it's, yep.
I have a stupid question.
No questions are stupid.
Can you, perhaps maybe you should repeat the question so that people online can hear it. What is the effect of metals again that changes the distribution? What is the physical effect again of metals? Is this stellar evolution 101, I'm sure, but can you remind us the effect of metals that
yes.
changes the distribution?
So the effects of metals
Fundamental physics
in the actual distribution. So then as you have more metals in your chemical composition of your cloud, you have more transitions available pretty much. So you're dissipating energy more efficiently, then your typical mass is just decreasing, and then you're forming low mass stars. Well, it's a very broad brush term, right? So in terms of the gas clouds, right? You're changing the opacity of the cloud, then you're allowing energy to escape more efficiently, things are fragmenting into smaller pieces, and then you form low mass, right? And dust and carbon grains, they just facilitate that, right? But that doesn't mean that you cannot form a low mass star just out of hydrogen and helium. It means that it's very difficult, but it's not impossible. At least that's what some people believe, right? And this is what it's showing here. And what I like about this is that this one gives us some sort of a redshift scale, which I like, right? I just made some basic math here with one cosmological, some sort of a framework Z equals 35 would give you 80 million years after the Big Bang, and Z equals 5, 1.2 billion years. So what this is telling us, this simulation here is showing for some sort of a given set of particles, it's giving you the mean metallicity as a function of redshift and the maximum metallicity as a function of redshift for all of those simulated particles. So what this is telling us is that, say, between redshift 35 and 5, meaning the first billion years of the life of the universe, in principle, you formed a lot of the metals that we see today, right? You enriched your universe from pretty much no metals, right? So this is a log scale, right? All the way to -3 over here. And what's interesting about this is that at the very same redshift, I don't know, 25, you would have stars with metallicities -4 all the way to -1. Meaning that if you look at a star today that it's a metallicity -1, in principle, if you believe the simulation, it could be a true second generation star. Because when you have a universe at redshift 35, the universe is so inhomogeneous at that point when the first stars are exploding that if a supernova explodes, depending on the geometry of the explosion, in principle, you can have places where there are a lot more metals than other places. So that's why you see this region here, right? And again, this is very interesting because in principle, when you observe these really old stars in the Milky Way, you could in principle be probing a very, very, very young universe, right? And what this is showing here is just the star formation rate for simulations of the halo and the bulge and the stellar mass function. I won't go into details here. What I wanted to show you is this bottom plot here that is telling us what is the probability of us observing today one metal-free star in the Milky Way, a solar mass or 0.8 solar mass metal-free star. And according to the simulation, what you would have to do is you would have to point your telescope to the halo of the galaxy, right? You would have to observe 1 million stars with 0.6 solar masses. And if you cannot find a single one of them that it's metal-free, that means that they don't exist, right? So we're not there yet, right? Maybe you have hundreds of really, that low mass star in the halo, maybe hundreds, a couple thousand, but we need to reach at least 1 million so we can start to make some sort of a quantitative statistical, some sort of conclusions about this. So this is what interests me, right? Because we need observations to just confirm the theory, right? So, the last thing I want to show about this is that, well, this paper actually came out a couple days ago on the archive, or maybe last week. This star over here, this is very poor, sorry. So this here, there's a star here, I don't know if you can see, and there's an arc here from a gravitational lens. So they actually observed a star that was really in the arc of the gravitational lens. So the magnification was such that they were able to measure the redshift of that star, and the redshift 6.2, and JWST recently got narrowband photometry for it. And based on the narrowband photometry and the models, it seems that this star over here is a luminous blue variable at redshift 6.2, right? This is just photometry. So what they're doing is there will be spectroscopy later this year. And if they do spectroscopy, and if they cannot find any metals in there, well, there you go. So then you have a population tree star. So this would be one of the very first stars to be born in the universe. And if they find metals, well, then it's the second generation, meaning that the first generation should be as old as 6.2 at least, right? You have to give time for the first generation to evolve, right? So this is super exciting. They had observed this with the Hubble Space Telescope, and now we have JWST, and then they'll have the spectrum very soon. All right, so this is the framework for the population tree. So then what we do, or what I do and people who work on the same things, is that what we call near-field cosmology, right? Which is the really unexciting universe that lies at z equals 0, right? We do redshift 0 things, assuming that, well, we had that really first generation of stars, hydrogen and helium, massive stars formed, exploded, injected metals into the interstellar medium at different amounts, depending on the mass, depending on the model. And then you have your second generation here, which we should be able to observe today in the Milky Way. As simple as that, right? Very, very, very simple. So how you would observe those stars is we need a spectrum, right? There's no way around it. If you need chemistry, precise chemistry, you need to have a spectrum. And just so you understand how unique those stars would be, this is a spectrum, in a shell spectrum of a solar type star. See how many absorption features we have? And here on the bottom, this is a typical, what we call an ultra metal poor star with a metallicity -4. So that's 10,000 times less iron over hydrogen than the sun. And you see the difference here, kind of same temperature, right? So this is a fair comparison. So you see that there's almost no lines in those spectra, meaning chemically pristine. Still second generation, but chemically pristine. And the question we are trying to answer is, well, how do we go from hydrogen and helium in the Big Bang all the way to the thing we see today, right? This is this astrophysical periodical table at z equals 0. At z equals 20, the mixture here was fairly different than this, right? We didn't have all of those, exploding white dwarfs yet. We didn't have AGB stars really early. So this is z equals 0. So we want to explain, well, why this is the way it is, right? And the theoretical framework for all of that, it's very old, right? If you know your history by now, you know about this review, which is 65 years old now. Unfortunately, the last surviving author, so Margaret, passed away, I think, 2 years ago. So now they're all gone, but the contribution is still here, right? If you have the chance, please read this one. This gives you all the framework that you need to know about how do we go from hydrogen and helium all the way to uranium, right? And what's interesting about this, I don't know, well, you won't be able to see it, and I'll read it over here. The very last part here, they say, and I quote, ejection of material from stars and the enrichment of galaxy and heavy elements. So they do give you a framework as to why and how the universe goes from chemically pristine all the way to everything we see today. So this is really highly recommended. So back to the spectrum. So we have to find these guys, right? We observe them, and I'll talk about the observations on the second part. So what you want to see, ideally, is you want to see a really flat spectrum, right? And this is one star with a metallicity -7. So really, really chemically pristine. However, the metallicity is only an upper limit, which is even better. However, there's carbon in the atmosphere. So this is no self-enrichment, right? Meaning that carbon came from the cloud. If the carbon came from the cloud, then there must have been a previous generation, right? Again, second generation then. But still very useful, because then we're pushing the limit in terms of that transition between population 2 and population 3. And people, like myself, we're trying to observe as many of those stars as possible, and we'll see in a moment that it's very, very difficult to find them. And one thing you see is, as you go to these lower and lower metallicities, the carbon actually becomes more evident. And you see in other papers here, this is from 2014, now in 2018, in all of those stars, even as you go to really, really low metallicities, you still see the carbon signature, right? So the carbon is very prevalent in those stars. It's not 100% like some people believed in the past, but it's still very prevalent. And it goes on, right? So this is just an example of the spectrum of that star. See? This is all continuum, so there are no lines in there. You see hydrogen lines, so this is the Balmer series, as you would, because the star is almost all hydrogen. But you also see, you see CH, so you see carbon, you see oxygen, you see some nitrogen, you see magnesium, you see calcium. So there's metals in there, right? Not a lot, but some. So the metals need to come from somewhere. So the signatures are everywhere. So these are just a couple of examples of really kind of an ultraviolet in the optical spectrum. And they all have lots and lots of carbon. So the story is the carbon is a really important ingredient in that sense. And again, the reason I'm putting this is because, in my mind, we always need to acknowledge the history, right? And this is not new, right? Nobody invented this over the last 20 or 30 years. This here, and this is 1963, right? Chemical composition of 2 carbon stars. And what they say here, the high-velocity carbon stars appear to be deficient in metals, but rich in carbon and heavy elements. So it's there, right? This is 1963. It was already there. This is another one from 1956. They say carbon stars, he says, carbon stars in astrophysical enigma, it is shown that these stars do not comprise a homogeneous group. Again, the information is there. It's not homogeneous, meaning you have varying levels of carbon giving you kind of the same answer about this early universe. And what's interesting about this, if you read long enough, at least in the abstract, you will find a reference from, believe it or not, 1899. And if you know how to use ADS, then what do, you search for that one. See? 1899, on the spectra of class, stars of class 3b. This one here, and I won't go too far on this, I promise, but I find this really exciting. BD plus 85332, right? Here, what this person says in 1899. The green zone is the brightest, meaning less absorption, brighter, right? So the green zone is where some of the metals are. So if it's brighter, means not a lot of metals, so metal poor. See the next one, band 9, strong and broad. And I think band 9, it's a CH or C2 band. So what this person is saying in 1899, that he found a star low in metals and rich in carbon. 1899. And then 1985, almost 100 years later, hey, carbon and related stars, the very same star, lots and lots of carbon, not a lot of metals, some evidence of S process for a different kind of a binary system. And then again, 1994. So nothing new, just so you understand how old this is. And people were already looking at those things, right? So between then and now, this is what the community was able to do. So this is just showing between 1998 and 2018, what the community that studies low metallicity stars, many of us included in the audience, what are the contributions in using high resolution spectroscopy. So this here, x-axis is your metallicity scale as a function of your carbon abundances, right? Usually, if you look at a galaxy, random stars, of course that the ones that are high metallicity would be overwhelmingly larger in numbers. These are really biased samples. People want to observe low metallicity stars. That's why you don't have a lot of here in the solar type, because these are uninteresting for this type of work. So if you've never seen this before, again, in 20 years, we observe about 1,600 of those. And remember the number I told you, you need about 1 million of those if you wanted to make some sort of meaningful conclusions about, the nature of the first stars. So we are still, again, that's job security right there, right? I'll have a job for the next 50 years if I want to, just observing these, right? Assuming people are willing to pay for it. Yeah, so if you look at this, you've never seen this before, you can kind of see, right, decreasing trend as you go. Let's assume that this is a time scale or a redshift scale. Local universe, this is today, and this is kind of a pristine universe. So you see some sort of a downward trend here, which people like to say this is your standard, galactic chemical evolution. So the galaxy is evolving, things are mixing, getting larger. There you go. There's a blob here, right? And there's kind of a plateau here. So as you go to really low metallicity stars, all of those relations break. And this kind of gives support to that hypothesis I made about, well, things were really inhomogeneous in the early universe. It's kind of it's almost like a stochastic process, right? Depending on where you are, that dictates what your metallicity will be, which today it's still true, but not as true as it was in the early universe. So if you make some smart divisions in this plot over here, this is what you see. Just the scale changed a little bit. So the stars over here, they're really high in carbon, and they also have lots of barium. And we know what this is. We know that these are binary systems, some sort of AGB type star. So we don't look too much for those when we're talking about first stars and the carbon-rich thing. These are what we call the carbon normal or carbon intermediate. So following, again, quoting galactic chemical evolution. And then you have those what you call carbon-enhanced, metal poor, with no other enrichments in heavy elements. And these kind of follow this weird plateau. So we are interested in finding more of those stars over here, right? And as you can see, so the line that we have here, and I won't go through the simulation again, this gives you what we consider to be the carbon-rich stars. So as you go towards lower metallicities, the fractions of carbon-rich stars tend to increase, right? And this is what we see, some sort of empirical evidence. So here is things from 2005 all the way to 2022. and this was recently published, as you go towards lower metallicities, the fractions of carbon-enhanced stars increase, right? So again, it goes back to the beginning, right? As you're going to a universe which is more pristine in terms of overall chemical composition, if you close your eyes and get a star, chances are it will be carbon-enhanced. And this is no coincidence, right? That doesn't mean that all of them would be. The fact that you see 100% here, this is an observational bias, I'm sure. Since we're looking for them, chances are we're observing the types of things that we're looking for, right? But not all of them are, and I'll show you more about this in a moment. So this is what's happening in the halo of the Milky Way. If you go to ultra-faint dwarf galaxies, hey, same behavior, right? I won't go into that into detail, but again, same behavior, same kind of a overall chemical enrichment type. And again, know your history. This is not new. 1985, right? This is Ursa Minor dwarf spheroidal galaxy. This is halo of the galaxy. So this is kind of a metallicity indicator and carbon indicator. So what this person, Nick, was trying to sort of conclude is that for a given metal enrichment, if you go to some sort of a more pristine environment as a dwarf spheroidal galaxy, your carbon would be a little bit higher overall. It's a very interesting paper. That is just to give you an idea that people were thinking about this for a long time, right? And then at some point, you get all of those stars in the Milky Way, and you have to start connecting the dots. And one way of connecting the dots is, well, let's try to do a model. So people try to explain the lack of stars in this particular region here to insufficient dust cooling. Again, back to slide number 5, right? Not enough metals, not enough dust. You cannot cool the universe or the gas cloud enough to form low mass stars. Then you have this big void here. However, if you have some carbon grains, well, maybe you can form some things, right? That starts at -7. So you can connect this with some sort of a more theoretical work. You can also connect the stars in the Milky Way, you know, the near field meets the far field cosmology with this damped Lyman alpha systems, right? I won't go into detail, but you can think of this, you know, a gas cloud at really high redshift, right? So you're just collecting all the absorption between the quasar and you, and when you measure the absorption features and you measure the chemical composition, in this case here, I think it's at redshift, oh, it's over here, redshift of the absorptions at redshift 3, and you compare the stars here is just chemical composition of stars in the Milky Way, and the black squares are just the composition of the damped Lyman alpha system. And they actually match. Well, plus or minus, right? Match is kind of a loose term in this case, but they do match somehow. So meaning that there is a connection between the near field cosmology and the far field cosmology. Another connection that we can make is we can observe those ultra-metal poor stars in the galaxy, and we can compare the chemical abundance pattern of those stars with predicted yields from supernova explosions at zero metallicity. And this is what people have done for many years now. And you see that in all of those panels, all of the dots are just the measured abundances in different ultra-metal poor stars, and all the lines are just predictions for supernova explosions, zero metallicity population tree explosions. And you see that, well, in some cases there are good matches, and most of them, these are supernova and hypernova, really high massive, mostly 20 to 30 solar masses. Assuming that they exploded in a metal-free universe, injected metals into the interstellar medium, and those stars here were formed. And what's interesting about this particular paper here in 2019 is that they compared spherical explosions with non-symmetric jets. And actually, surprisingly, one of the models that matches, you know, the best with the data is actually the asymmetric model, meaning that if you were in the right place when the supernova exploded, if you're here or if you're there, then your chemical composition would be vastly different, which some people may think is a kind of a stretch, but well, it's a explanation until we have a better one, right? So once you do this, again, if you had enough statistics for all of that, we have about 30 of those since 1998. So what you can do in principle is say, hey, if I have a slice of metallicity here, and if I can look at all of those stars and predict what the progenitor mass was for the previous population, I can in principle say, well, maybe I have some constraints on an initial mass function for that population tree. And this is what we have been doing, again, one by one. This is one by one, you know. And what we have here so far is most of those progenitors are massive, between 20 and 30 solar masses. We have maybe about 30 now, which is not enough. But in principle, if we have 1,000 or 1 million, we would be able to say, hey, we know that today our initial mass function, well, depending on the author, you have something like this. But what happened at z equals 10 or 20? How was the shape of the initial mass function back then? Right, so then that's what we're trying to do when we observe all of those ultra-metal poor stars, right? So, so how early is early when you talk about matter enrichment? So this is more or less the same graph that we saw before, but now I just introduced a very nice, some sort of a redshift and age scale here as a function of the metallicity. Just using kind of a rough term, so don't believe this to the letter, right? But it's just to show that if you make a cut here at -4, you're still at kind of a redshift 25, and the universe is still very, very young. And all of those stars here, I'm pointing those two here because they have a really low carbon abundance. Both of those were discovered last year. And if you make a cut here, a vertical cut, see that the carbon here is at 8, and the carbon here is at 4. So these are 4 orders of magnitude. So it's a factor of 10,000. Same amount of iron, 10,000 difference in terms of carbon, right? So very, very different, very inhomogeneous in that sense. So what we want to do is we want to find more of those, right? So that's the game. So we want to find more of these. And I'll spend, well, the remainder of my time just trying to convince you that this is something worth doing, right? Well, I think it is, but you should also think as well. So how do we find those? The ones at -4. They're really hard to find, right? So this is from, I should have put the reference, right? I think this is Penn stars, right? 100 square degrees here. I don't know how many stars you have here. But if you make a cut in magnitude at 18, among all of those here, you'll probably find just one star at metallicity -4, right? So then you don't go to a telescope time allocation committee and say, hey, I want to observe about 3 million of those, and I'll find one of them that it's interesting, right? So give me all of your time to do that. So that doesn't work, right? It doesn't work. So you need to get smart about how do you go from maybe 1 million stars, maybe I can select those down to 100 maybe, and if I can find 1 in 100, it's a lot better than 1 in 1 million, right? It's a lot easier to convince people. And what I like to do when I show this is that people used to say that an image is worth 1,000 words, right? You know about this, of course, if you look at Andromeda here. And if you go on Wikipedia, well, there's a lot of information here, but the image is kind of a lot more impressive, right? So my take on this and my extension to the metaphor is the spectrum is worth n images, where n is kind of your resolution element over here, right? So then what you need to do is you need to decide what is the ideal n that you need in order for you to get the information that you're hoping to get, right? Because if you have a if you have a low n, then it's kind of a cheap, right? You don't need a lot of time to observe, just a couple images. But if you want a high n, high resolution, you need a lot of time. So then you need to find a compromise between imaging and spectroscopy. And what I have here, maybe some of you have seen this already. This is a really high resolution spectrum. It's about 30,000 resolving power. And what I'm doing here, I'm just degrading the resolution. And if you can look at the dispersion here, the dispersion is increasing and your signal to noise is increasing as well, right? So you see that you still see some shapes. You still see, absorption features. You see carbon bands. You see calcium lines, all the way to really high dispersions. So you need to decide where you stop this simulation in order for you to ask time on your telescope, right? So depending on what you want to do, if you want to measure uranium in the surface of a star, you need high resolution. In my case, or in our case, we want carbon and metallicity pretty much, right? If I have those two, I have enough to just get started. So in principle, I don't need that. I need something like this, right? Which is, coincidentally or not, narrowband photometry can give you something like this, right? If you go low enough in resolution, you can get enough information to get carbon and to also get metallicity. And this is where one of those surveys that, well, people here at IAG and other places participate, the SPLUS survey, well, the Southern Photometric Local Universe survey. I'm sure you've heard about this already. And I won't go into details. I'll just say that, well, the robotic 80 centimeter telescope is here at CTIO, and this is the footprint of the survey so far. So what this survey is doing, and I won't go into details as much, is that it's just observing the entire sky with 12 different filters, right? 7 of those are narrowband, and 5 of those are broadband filters. They're all over here. And overlaid on the filters here, this is a synthetic spectrum of a low metallicity star. And I'm sorry that it's not too visible to you, but if you look at the calcium lines here, these are the lines that give us some sort of a metallicity indication, right? So they're really centered on this narrowband filter, and then you have the carbon band here on this one. So in principle, you can isolate those features just by doing this narrowband photometry. So instead of observing that entire spectrum, you actually have 12 pieces of information, right? A medium resolution spectrum like this would give you, I don't know, in this range, it could give you maybe 6,000 points or something like this, but SPLUS gives you 12. So then see if with 12 points you can get meaningful information so you can ask for the 3,000 later, right? And this is what we're trying to do. So, and this here on the right-hand side is just some kind of a provocation, because when you look at extended objects, if you look at all of those 12 filters, you can actually see how structure changes in galaxies when you're looking at different filters, right? You can see H alpha, you can see all types of structures, you can see arms, you can see star formation regions. But if you look at a stellar field, this is pretty unimpressive, right? This is borderline boring here. You don't see any changes in the actual stellar field, right? But that doesn't mean that there's no information there. And this is what we are trying to do. So when you look here on the left-hand side, these are synthetic spectra with different metallicities. So as you go towards lower metallicities, the strength of your calcium line decreases, right? So as you can see, the line decreases, and as the line decreases, it changes the emerging flux of the star, and then it changes what we call the spectral energy distribution, right? See here? So for a given temperature, if you change the metallicity, you actually change the magnitude of the star significantly. And if you can capture that information in a meaningful way, you can actually select stars of different metallicities by just looking at the emerging flux on that narrow band. And this is what we do. And on the right-hand side is just comparing this narrow band filter from SPLUS and how the equivalent width changes. So the area here changes as a function of the metallicity, and with a broad band filter from SkyMapper, for example, right? So this here is able to capture a lot of those changes in there. You can play with those 12 filters if you want. We've done some work with artificial neural networks. You can do whatever people doing machine learning do, right? You can do random forests. You can do whatever suits you, right? You have input information from photometry. You have output information from spectroscopy. I'll give you this. You give me the answer, right? It's kind of a learning problem in that sense. So we've done that. We were able to do very accurate temperatures, very accurate metallicities and carbon abundances just by looking at photometry. Again, just by looking at those 12 points. And we can extend that, and this is what we have been doing recently, is that instead of going really fancy on the machine learning techniques, what we try to do is just looking at color diagrams. Everybody knows color diagrams, right? And you know that depending on where you are, you're getting different information from the stars. So we happen to find a very crazy color combination in X and Y axes that would separate stars of different metallicities, right? So this is just a density plot from SPLUS DR3, but here on this side, the black points are low metallicity, -3, and the blue points are high metallicity. And you see that there's a metallicity trend, right? You can see that well. So if I want to find the interesting ones, where would I go? I would focus here, right? Because chances are, if I observe 10 stars here, maybe one of them would be interesting. But if I do this here, maybe it'll be 1 in 100, right? So you use those color diagrams and isolate the ones you want to find. And this is what we've done, right? We isolated them. We observed 500 of them using the Gemini South telescope in Chile under poor weather conditions. And we also used the Blanco telescope, also in Cerro Tololo, using the Cosmos spectrograph. So we observed about 520 stars, again, just by doing a color selection. We observed 500 of them. This is, again, just the magnitude distribution in the 12 filters. We observed things that are fairly bright. So let's see, G magnitude of 12 all the way to 17. So this is a good range of magnitudes that the telescopes would allow in some sort of a reasonable exposure times. And this is what the spectra look like. I'm sorry that it's really small, but this is just showing 100 spectra of the 500, just as an example. And you see that you can get a lot of interesting information. So these lines here, they are metallicity indicator. The band here is your carbon indicator. Then you have alpha elements here. And this is how they look in terms of their temperature as a function of the surface gravity. So this is some sort of an HR diagram and some isochrones and the metallicities here, just so you have an idea of those 500 stars. And since you have spectra, right, you have lots of good information. You can get interesting, carbon abundances. See, you can get carbon abundances. You can have abundances of alpha elements, in this case represented by magnesium. And, well, again, 500 stars, right, more or less. And we did find 2 here. There are metallicities below -4. So instead of 1 in 1 million, we have 2 in 500, which is pretty good, right? Well, maybe not pretty good, but a lot better than 1 in a million. So we did find 2 of them, right? And you can see that, and I won't go into detail, but I really like this plot, is that this is what we call the spectral energy distribution, right? We have the 12 points for a bunch of stars here. And if we scale all of those to a common Z magnitude, for example, and restrict the temperature range very narrow, see, between 4980 and 4998, all of the change that you see on the blue filters is due to metallicity. And you can see this here, right? Metallicity minus 3.5, this is the spectrum, really tiny line. Metallicity minus 1, strong line. And this is what you see here. The ones on the bottom, there's a lot more absorbed flux in the blue bands, lots of metals. The ones on the top, little absorption, metal poor. These are the ones we want to find. And, well, you can ask, well, how good did we do? Well, I think we did pretty good. So among those 522 stars, 92% of those had metallicities below -1, and 83% of metallicities below -2. Again, if you were doing this randomly, instead of 83%, you would probably have 2%, right? So meaning that, well, 83% of all the stars I observed are below -2, which, again, gives you all sorts of interesting things when you're doing statistics on low metallicity stars. And, well, as everybody, if you're trying to improve on your own work, then you have to compare with your own work and tell people that you're doing better than you did a couple of years ago. So we compare the work with the stuff that we all did, over the past 3 to 4 years, and you see that if you want to find low metallicity stars, this is just a good way of finding it, right? Finding them. Maybe it's not the best way, and it's certainly not the only way, but it's a good way, right? And it gives you a lot of interesting information. And you can even do further cuts if you want. I won't go into detail on this, but in principle, if you play with more colors, you can increase this from 83 to 88% for stars below -2. So that's pretty good, right? Because then you're able to find more interesting stars. And this is what we find. We found one very interesting one, and this one here in pink. And again, this is the same color diagram you saw before. And this star over here, again, in the middle of those 522, this is a star with a metallicity below -4. So this is what we call an ultra metal poor star found among those 500 stars. And this is the result of all of this work, right? We start with photometry, really low resolution narrowband photometry. So you have 12 pieces of information for that star. If you're able to use those 12 pieces of information in a smart enough way, you go to a Gemini telescope, for example, and you go from resolution, your resolving power from 30 to 1500. And you observe that star for 5 minutes. Again, 5 minutes on an 8-meter telescope gives you this spectrum over here. This is a defect, so it's not an absorption. But you can clearly see the calcium lines. So you can calculate metallicity and say, oh, interesting enough. So then you call your friend who has time on the Magellan telescope and say, hey, do you have an hour to spare? It's a very interesting one. Oops, what did I do? Nope. How do I get rid of this? Oh, see? Okay, so then you call your friend and say, hey, if you have an hour on the big telescope, just give me a really high resolution spectrum. So you go from 1500 all the way to 30,000. And then then it becomes really fun, right? Because you have hundreds and hundreds of interesting lines to measure. And then you can measure carbon, nitrogen, oxygen, and all the, mostly the light stuff, but you can even get to barium. And we got to barium and strontium on this one. And this is what you find. And then when you look at this, the combination of all of this, and I'm almost done. Well, I'm actually on time. That's good. So the power of all of those methods is you start from your narrowband photometry, right? And again, it doesn't have to be SPLUS, any photometric survey, right? SDSS, PenSTARRS, Gaia, so all of those are very rich in information. You only have to know where to look, right? So you start here, 20 million objects, narrowband photometry. What you do whatever you want, color diagrams, you do machine learning, and you narrow down from 20 million. And in this case, I'm just talking about Gemini here. You go to 138 or 500. You observe those, and you get the spectrum and say, hey, these are interesting or more interesting than the other ones. And then you choose one or two, and you go to in this case, it's a slightly smaller telescope, but with a high-resolution spectrograph. And you get enough information, and you find a star. In this case, was a very pristine star that gave us a lot of good publicity. Again, from 20 million all the way to one star, right? So that's all the story that I wanted to tell. I just have one more slide, but I think the lesson here is, if you want to talk about how the universe evolved from being really chemically pristine all the way to having all the metals that we have here today, you need to find that observational evidence, right? And what this is doing is just giving one tiny piece of that puzzle, right? What I'm telling you is that I can observe a star in the Milky Way today that has a chemical composition that agrees with a population tree star with 20 solar masses that was formed out of pristine gas, maybe at redshift 25 or redshift 30. That's one point, right? But if enough people do that, and then 50 years from now we have 1,000 points, well, that's good, because then you're constraining that IMF even further, and then you're giving some sort of information for people doing theory. And hopefully with JWST, right, it will solve all of our astronomy's problems, well, as I was told. Yeah, as long as you don't say the actual name of the telescope, you're fine. Then you probably see those stars in situ, right, as well. You see really the population tree stars in there if they're bright enough for you to observe them. So in conclusion, and I'll leave you with my last slide, is what's next for carbon is, well, you keep observing them, right? I think you need to build statistics, right? There's no way around that. And especially because, well, until until 2021, we didn't know that those ultra-metal poor stars could be that carbon poor. This is 1 year ago, right? If we keep observing them, maybe that range will be even larger, or, well, it cannot be narrower now, but maybe we'll see what the fractions are, right? So we need to continue the high resolution follow-up. And to me, the best thing is that, well, the more we know, the more we understand how little we know, right? Every new piece of information we get on this regime, it actually confirms some things that we believe, and it actually says, well, you're kind of wrong here, right? But, so you just needed more pieces, right? You just need more pieces. And this here, again, this is just one piece, because at the same time, we're doing this incremental science, right? Just building statistics, and there's nothing wrong with that. But again, the payoff is usually on a longer time scale, right? You have the nice discoveries that give you press when you find a really nice one. But then if we integrate that over 20 years, then you have 1,000, and that's the incremental science that we all need to do. And yes, I'll leave you with that, and I'll take any questions you may have. So thank you for your time. And I hope it wasn't too bad with the mask, but
Thank you, Vinicius, for your very, very clear talk. If there's anyone with questions, Professor Laerte.
Why carbon?
Well, I think it's the first element in the periodic table, at least after, if you take lithium, boron, and beryllium out of the equation, that's the very next one, and it's one of the most, the more abundant ones. We can also do nitrogen and oxygen, so they go together, but nitrogen and oxygen are very hard to measure. You need some sort of more things in the ultraviolet, close to the UV cutoff, to get good nitrogen abundances, for example, and oxygen. Carbon is very easy to measure in optical spectrum, even in low resolution. So that's one of the things. So the signature is strong, and it's easier to measure than the other ones as well.
What about magnesium, for example? Because magnesium has optical bands that are very strong.
Same thing, yeah. So I didn't say anything, but all of those have high, well, not high, but they have, you can measure magnesium. You measure on the triplet, on the narrow band as well, you see that, but yes, magnesium as well. Not as strong and as evident as carbon, but still, yeah.
No, there is a question by Betty. She'll make this question via Google Meet.
Mm-hmm.
Hi, Vinicius. Very, very nice talk. Wonderful review. Can you hear me?
Yes.
Okay. So I have two questions. One regards what is the maximum mass of the stars in your survey so far? The maximum mass that you get for these very, very poor metal stars. And the other question is, what about other wavelengths? What can we, what kind of, can you get more information on metallicity from other wavelengths nowadays? Or yes, what is the current situation?
Mm-hmm, mm-hmm. Okay, so the first question, the answer is, we usually assume that those are about 0.8 solar masses. For this sample that we have 522, we are trying to estimate the masses, and they're all low mass. So you wouldn't find any of those with above 1 solar mass, I don't think. So they would all be 0.6, 0.8 to 1 solar mass, because some of those are still on the main sequence. We do have some subgiants and red giants, but most of them are low mass in general, because otherwise, if they were born in an environment with a metallicity -2, and if they had 2 solar masses, they would have evolved already. So they wouldn't be main sequence or giant, right? So that's one thing for this particular sample.
Yeah, in the local universe.
Yes, exactly. Yes. Mm-hmm. So for the second part is, we usually do things in the optical, especially for this validation, so the metallicity and the carbon abundances, because it's very easy, and it's very inexpensive in that way. When we go to the ultraviolet, and the only thing we have is COS and STIS on the Hubble Space Telescope while still flying, we can do lots of our process there, mostly our process. Because so for carbon and metallicity only, or the light elements, the optical is the best window, right? There are lots of works that do things on the near infrared, right? So you have Apogee, and you have people doing spectroscopy on, JA, JK bands, and even in the Y band, and you can still get. Sometimes the near infrared is a little bit better for molecules, right? You have lots of OH, CH, NH bands in there, so you can get CNO a little bit more accurately. But most of the work, it's done in the optical, because it's easier, right? Even for data reduction, and it's a lot easier, and the signatures are very, very clear there, even at lower resolutions.
Right.
Thanks, Vinicius, for the nice talk. I got very interested for one point you explained in the beginning about the theoretical studies. So you mentioned also in connection with the observations that you see it's very heterogeneous, the metallicity of this second population, and you mentioned that it can be due to the asymmetric explosions of supernovas or something like this. So my question is, in these studies, it's not clear for me if this is a hypothesis from the scenario that maybe the mixing of the metals in the material that is contaminated by the supernova is not efficient, or it comes as a result from the observations that this mixing is not important, that it's not mixed after it's contaminated.
No, it's a very good question, because in many of those models, the mixing is actually a free parameter. So it means you can do whatever you want with it, right? So you can make it fit your observation, and then you can try to explain why it did fit, right? So it's tricky. And many of those, again, you mentioned the mixing. Some of those assume that there is instantaneous mixing, which we all know it's not true, right? That there's some time scales as well, right? So there's lots of hypotheses there. So many of those hypernova models in particular, they have lots and lots of free parameters. And what people try to do is, if you trust your observations enough, then you make your model fit, and then you try to explain why it fit, right? That's one approach. The other approach is, I fix all the parameters in the model, then I fit those with the observations, and if they don't fit, then you have to explain why. Maybe we have problems in the observations as well, right? We have some elements that are not very easy to measure. We have, again, for all of these stars, most of those we assume that the atmospheres are just one-dimensional LTE atmospheres, which is not true, right? They're all 3D non-LTE effects that we need to take into account, and people are starting to do that now. But I think we're still very early in that. And I think the short answer to the question is there's lots of free parameters. So people tweak that and try to explain why. And mixing is one of them, right?
Thank you.
Yeah.
Okay, Vinicius, I have a question. Professor Melins.
Hi, Vinicius. Great talk. Regarding the mass of the progenitors, so you said that all these progenitors should have very high masses, right? But then when you try to look for the progenitors, then you said that the most massive are about 30 solar masses, I think, right?
Yeah.
So do you think it's just a matter of observing like 1 million stars so that we will observe the really massive ones, or not?
I think so. Right? I think it's still a matter of we don't have enough statistics. However, one thing that we do acknowledge is that at least one of the models we use, the faint supernova models from Alex Hager, for example, this is one type of models for faint supernova, right? And it may be the case that in the very early universe, you had the faint supernova and you had the spin stars, for example, the ones with high magnetic fields and they're spinning. So maybe the fact that we are not finding super high masses for one model, maybe it means that the progenitor was of a different nature, and we're trying to fit on this model here. But I think it's still early to know because we just don't have enough stars, I think. And again, that's my opinion, right? Sometimes people disagree with that in the sense of the number of progenitors that we would have, but I think that's the way I see it. I think we have a lot, but we're still really far from having some sort of definite answers for that.
Okay. Does anyone have any other questions?
I have another question, because I have seen a lot of interesting talks about the studies of dynamics in the galaxy, so kinematic properties of the stars. Is there some way of using also the, I don't know, dynamical information from the stars in the halo for helping you to constrain even more these stars where you are looking for these low metallicity targets?
Well, and again, folks here would be able to answer that maybe better than I can. So the kinematics, and if you can find the origin of that star in terms of, well, you can trace back the ultra metal poor star to some sort of a population of stars that share the same chemistry and the same kinematics. Maybe if you have that, you can say, well, this was a mini halo of X solar masses that was formed with a pristine gas, right? Maybe you can try to trace that back to the redshift. Yeah, so more information gives you a better idea. But in the end, if you go far back enough in metallicity, you know, I don't think those structures would, not even those structures would be formed still, right? If you look at a star at -7, maybe it was just formed there and it didn't have to be associated with any type of coherent structure just because it was really, really early in the life of the universe, right? But again, the work, you know, folks like Guilherme and people here do with the kinematics, it helps us understand how those stars were mixed in the galaxy, right? It fits the bill that, well, none of those stars were born here, right? It's not that, well, there was a gas cloud in the halo and formed an ultra-metal pulsar. It's not the case. So they're all extragalactic origin. So that's giving us an idea about the history of the Milky Way in terms of, you know, early galaxy assembly. But then I think what we are trying to do here with the chemistry, it's going even further, right? Even before that time, when you go at those really, really pristine stars.
So does anyone have any other questions? Okay, so let's thank Vinicius once again. And see you all next week for another seminar.
Deu tempo certo, né? Aí, ó.
Deu.
Até que foi.
Tá ótimo. Eu ia perguntar...